All right, we're going to get started with this pre-recorded lecture on discretely braced beam design. As of now in class, we should have already done one example with discretely braced beam design, and so this example is going to cover the next one. And particularly, we're covering something looking at false positives that can be associated with beams of high shear, with a high CB value. I'm also going to talk a little bit about shear. We've been using just the blanket value that's in the table 3-2 for the FEVN calc, and I kind of want to introduce a little bit about how that works, just so you have an understanding of the spec. Now, I'm probably going to go a little bit fast today because we're on YouTube, and so it's just me, but that's the beauty of YouTube, is that you can always just pause and rewind if needed. As for housekeeping for the class, I will most likely have the attendance grades up to date by the time you watch this. But the update on the homework and what's graded and whatnot, I'll just wait till we have class on Wednesday. Okay, so let's get into the lecture. And first off, I want to talk a little bit about the process for discretely braced beam design. By now, we should have all used this process to select a beam in our previous lecture, but let's just recall this to make sure that we're good with where we're at. So the first thing that we do is our structural analysis. We compute the factored moment, and while we're at it, we might as well compute the factored shear. More often than not, we're going to need to use an assumed self-weight, and so whenever you're going to the through the design process, if ever you select a beam that's heavier than your assumed weight, you need to go and update your MU and your VU. Next, you're going to compute your moment of inertia based on your deflection limit requirements, and then you're going to get into the design process. You need to determine your LB value and your CB value that you need to use for design. If possible, try and use table 3.1, but if the moments or the loads are really weird, you just have to compute the CB value yourself. And then you go into table 3.10. And the way it works, as we've said, you go into the table with the LB on the x-axis. On the y-axis, you go in with MU over CB, right? Locate that point in the table, and then you're going to go up and to the right and pick your trial section. Once you have a trial section, make sure that it's going to meet your deflection requirements. Make sure that it's going to have an IX bigger than your moment of inertia requirement. If that's not the case, just go to table 3.3 and pick a section from there. Once you got a trial shape and you verified that moment of inertia requirement is most likely going to be met, then you can take that section and analyze it, and make sure you analyze for shear, for moment, for deflection, in order to ensure that that it meets capacity. Now, food for thought. We mentioned this a little bit in a previous lecture, but when we were talking about analysis. But what if you're in the design phase and you have a scenario like I mentioned earlier with some really wonky loads and some really odd bracing scenarios, and you have different unbraced length, different CB values, different moments. So if you're going to design this beam, you need to pick one of these segments to go into table 3.10. What I would do is pick the segment with either the largest MU over CB or the largest LB. Either one would be a valid approach to pick a trial shape. There's a good chance that's probably the same segment. And if not, I would probably just go with the one with the largest moment. Once you have that for analysis, analyze all of the unbraced segments to verify their capacity. So you're going to pick a trial shape based off what you think is the worst case scenario, but once you have that trial shape, analyze all the segments, all the FEMNs for all of the three segments, compare that against the MU for each of those segments. Now, it's possible that some of those segments may be neglected by observation, so you might see a segment that has a lower moment and a larger CB and a smaller LB, so it's like by observation, that segment's not going to matter, so just go with the one that you think governs. But if you're unsure about that, just check them all, because there's no reason not to. And remember, for moments, the segment that governs is the one that has the largest performance ratio or the largest efficiency. So just the FEMN for that segment as the denominator and the numerator being the largest moment that you find in that segment. So there'll be a performance ratio for each one. Now, what I want to talk about is a problem with high CB values. And I'm using the term high in quotation marks because there's really no set value that this is going to happen at, but you'll see what I mean when we look at the potential for false positives. And to explain that, I want to go through just a trial exercise with you. I think that any time that you get a chance to use table 310, the more practice you get, the better you're going to get at it. So let's look at trying to pick a section for the following data. Okay, so I have a moment of inertia requirement of 2,800 inches to the fourth. That admittedly isn't going to matter a lot right now, but I threw it in there just so that we have it. So, but we're picking based off of a factored moment of 10 20-foot kips, an LB value of 20 feet, but CB is 2. CB is actually pretty high. That's a pretty large CB value for design. So we've got our factored moment, we've got our CB, we've got our LB. So what we're going to do is we're going to go into table 3-10 with the following sections, or with the following data. We're going to go in with, on the x-axis with 20 feet, and the y-axis with MU over CB of 510. And you're going to pick a trial shape. Okay, what you ought to do is pause the video and see if you can locate that trial shape based on that data. And so again, you're going to go into the table, x-axis 20 feet, y-axis 510, find that point, look up and to the right, and find the trial shape. So you ought to pause the video and see what you can find. You should find a W24 by 84. That should be the section that you locate. And so again, what we would be doing is going into the beam charts. You know, I believe that the page that we're probably going to be on is something like, so 510 on the y-axis, and then a unbraced length of 20 feet. So I'm actually on the left page. I'm on 3-116. And you can see, yeah, 20 feet there. Yeah, you can see where the W24 by 84 is. Now, that's a trial shape. So the next thing we would do is go into analysis land. So we would find that shape in table 3.2. Now, if you go to table 3.2, you might say, okay, let's go to the W24 by 84 and start looking up some values. And one of the questions I want to ask is, what is the shape's phi-MP? What is its plastic moment capacity? And so if you want, you can pause the video and see if you can find that. And looking into table 3.2, you should find that for W24 by 84, the phi-MP is 840 foot kips. Now, the question is, does anybody notice a problem with this? And so you ought to pause the video again. I'm asking you to pause a lot during this, but you ought to pause the video and just look at the numbers on the slide and see if there's a problem. Because there is a problem, and it's actually pretty apparent. Let me advance to the next slide and show you what that is, but you ought to pause and see if you can figure it out. So here's the problem, okay? If you look at the section we just picked, remember the maximum moment is 10 20-foot kips, okay? We can go back here and see, you know, where we're picking a section for the following data. You know, look right here. The maximum moment was 10 20-foot kips, and look at this. You know, phi-MP is 840. So maximum MU is 1020 and the phi-MP is 840. So that's the maximum possible phi-MN. Remember, when you go into analysis mode, you're trying to determine phi-MN. And regardless of what zone you're in, if you're in zone 1, zone 2, zone 3, it doesn't matter. Regardless of what the math generates, phi-MN is limited to phi-MP. Remember that LTB curve. Remember, you have the LTB curve that looks like this. It goes over, down, and up. And then your CB value tends to, you know, amplify that curve. It would get bigger, but you're always cut off at MP. You can't exceed MP from a flexural capacity standpoint. So the section is no good. Let me erase all that ink. That trial section doesn't work. It's a false positive. See, what happened was this. CB serves, again, it serves to increase phi-MN, but it can't increase past the plastic moment. But you can't account for this in the design phase. Remember, table 310 is only generated based off a CB value of 1. So when you have a really high CB value, you can end up getting to trial sections that end up not working. So this is another reason why you must analyze a section once you nail down something for trial. Now, what happens when you get a false positive? So if you look here on the screen, this is for the case that we just looked at. So if you go back a couple slides or a few minutes in the video, you'll see that, you know, this is an LB of 20 feet and an MU over CB of like 510. So we went up and there's the W24 by 84. What happens when you get a false positive? just go to the next one, okay? So the next section might be a W27 by 84. Then go check that one, see what its VMP is. If that doesn't work, go to the next one. So unfortunately, in this initial phase, there's a lot of page flipping. And so one of the things I recommend is to maybe have 2 bookmarks, one to bookmark table 310 and one to bookmark table 32. So you can go to table 310, pick a section, go to table 32, look up its VMP. Go to table 310, find another section, go to table 32, look up its VMP. And so you'll just keep doing that until you find one that works. And as we mentioned in the previous lecture, if you can't find a section going this way, it might be easier to trace upwards, especially if you have a lot of lines that kind of overlap on one another. So that might be easier to trace upwards. If you also have a larger CB value, it might be a good idea to set up a table. So I'll show you kind of how that would work on a given example. So let's go back to what we were just doing. So we picked a W24 by 84. Remember that the MU value was 1020 foot kips, and we looked up a VMP of 840. We got that from table 3-2. Now, remember, whenever you get a trial section and you find one that works, you also want to check its moment of inertia against the minimum moment of inertia requirement. But for this instance, who cares whether or not the moment of inertia works, because the W24 by 84 is no good. So there's really no point in doing this until you have a section that has adequate moment capacity. So as I said, if you have a trial section that doesn't work, just go to the next one. So the next one was a W27 by 84. Again, our factored moment is 1020. If you go and look up the W27 by 84, its plastic moment capacity is 915. So it's no good. Again, no point in checking the moment of inertia because it doesn't work. And so then we say, okay, let's go to the next one. Next one is a W30 by 90. Again, must withstand a moment of 1020 foot kips, and its VMP is 1060. So now we have a section that's a viable candidate. Most likely what will happen is that because the CB is really high, the capacity is in fact probably 1060. But we won't know that until we go through the analysis. It's possible that the capacity still isn't good. Again, that's why you have to check. CB amplifies the capacity, but up until MP. You just have to check to make sure. Now, so again, we might not know that it works. You have to analyze it, but at least now it's worth doing the math and checking out. For the moment of inertia, though, we might as well pull that. Remember, we had a requirement of 2800, and the moment of inertia for a W30 by 90 is 3610. So we're good there. So this is one that's definitely worth looking at. Now, if we got to this point and the moment of inertia requirement wasn't met, I'd probably abandon table 310 altogether and just select a section based off table 3.3. What that would mean is that you have a beam that has really stringent deflection requirements, and so all this stuff about moment capacity, while you have to check your section to make sure it works, it probably doesn't govern your design. Your design's probably governed by the deflections. Design example, start to finish, just to make sure that we're comfortable with this. So we're going to design a discretely braced beam for the following section, or for the following beam. So we have a beam, it's simply supported, it's braced at the ends and at midspan. So the unbraced length is 10 feet. And if you notice, this beam is symmetric. We have the same CB value on both sides, the same factored moment on both sides, the same CB value, LB, MU. So we're only going to focus on one section for design. We don't have to check multiple sections. I'm assuming that the dead load is 100 pounds per foot. We're also going to assume that this deflection meets a live load deflection limit of L/360. And so you ought to go along with this problem with me as we're doing the example. Be prepared, because there is a lot of flipping back and forth. And again, this is what I was talking about, where you should have two bookmarks, one for table 310 and one for table 3.2, so you can do that. I kind of cheat a little bit in the notes that you're going to see here in a second, because I have the screen clippings from each of the tables inserted in the notebook, but you'll see that here in a second. So let me pull the notebook up and let's see what we can make happen. So here's the notebook. And so I'm going to try and go through the step-by-step process like we've been doing in class. Like I said, I'll probably go through it a little bit faster because, again, it's just me recording on YouTube. And I have all my calcs already pre-calculated. So the calculations might go a little fast, but you can always pause. And I really would suggest that you go through this with me to make sure that you're comfortable. So first off, I got to pull my draw button up. Let's see if we can minimize this a bit so I can scroll down. And let's go through our step-by-step process. So step one, we need to determine MU and VU, okay? So we have a beam that's simply supported. It's subjected to a uniformly distributed load for the dead load, and it's subjected to a it's subjected to a concentrated load at midspan, and that's our live load. So we have W naught is 100 pounds per foot, or 0.1 kips per foot. Remember, that is assumed. So that's definitely something we want to look at later once we pick a trial section, if that's something we need to refine. Now we know also that the L is 20 feet, so maybe I should put here L is 20 feet. So our dead load moment is going to be WL squared over 8. And so when you chug that out, so 0.1 times 20 squared over 8 ends up being 5 foot kips. And then our dead load shear is just WL over 2. And so when you chug that out, that ends up just being 1 kip. Now that's for the dead loads. For the live loads, we have a live load at midspan of 65 kips. And again, the length is 20 feet. So if you want, we can say that this is table 3-23. That's the table that lists all the analysis aids in the manual. This is case 1, and this is case 7 down here. So case 1, case 7. This is going to be, I think I can do better there. ML is going to be PL over 4. And again, you can find that on case 7. It's on page 3-210. So maybe I'll put that down here. Page 3-210. This one's page 3-208. So you can find that in the manual. PL over 4, so 65 times 20 over 4 ends up being 325 foot kips. And then VL is just going to be P over 2, which is going to be 32.5 kips. All right. And again, like I said, you can always pause and just you can always just pause and follow along with this. Give me 1 second. I'm gonna, if I can just move that over a little bit so it's not so squunched. All right. So we have a dead load, we have a live load, so now we can factor. And so factoring, we get MU is 1.2 M dead plus 1.6 M live, and that ends up being 526. Here, I'll put that over here. So MU is 526 foot kips. And then VU obviously is also 1.2 times dead plus 1.6 live, just the shears. And we get that VU is 53.2. Again, shear probably won't matter, but might as well do the calc just so that we have it. So there's our results from step 1. So we have our factored moment, factored shear. I think by now that should be pretty straightforward. Next up, we ought to do the deflection check. So for the deflection check, so what we're doing is computing required IX. So the first thing that we need is our deflection limit, which in this case is L over 360. Again, very common deflection limit for beams. So our length is 20 feet. we got to convert that to inches. Okay, so 20 times 12 over 360 ends up being 0.667 inches. And we compare that to the maximum deflection, which again comes from case 7, because this is we're talking about the live load. So we have a scenario where it's a simply supported beam and just a concentrated load at midspan. And that deflection is PL cubed over 48 EI. So what we would do is set PL cubed over 48 EI equal to this. So I'll do that over here. So PL cubed, and then don't forget your conversion factor, over EI, 48 EI, equals 0.667 inches. And so what I'm ultimately doing is just solving for the moment of inertia. And so the easiest way to do that is just 0.667, just multiply both sides by Ix, divide both sides by 0.667. And so I'm getting that Ix required is going to be PL cubed over 48E times my limit. And so that's going to be, what is that, 65 kips times 20 feet cubed. And then don't forget the conversion factor. E, hopefully by now that's burned into the back of your head if I wouldn't get ahead of myself. And then the deflection limit, here I'm going to scoot this camera back a bit so it's not all in my face. That's a little better. Okay, so that's a little better. Okay, and then the deflection limit is 0.667 inches. And so Ix required is, when you chug that out, you should get 968.3. And that's enough specificity for design. Okay, so give me one sec. Let me drag these down. Like I said, I have some of these already ready for me. And so I'll show you what's going on there. But basically, after steps 1 and 2, you should have everything that you need for design: a required moment, a required shear, and a required parameter to meet your deflection limitations. So step 3, select trial shape. And this is also kind of step 4 together, because we're also going to be checking to make sure that we meet our deflection limitations. And so just to be clear on how we do that, we're going to go into the table with an LB value of 10 feet, and we're going to also be going into the table with an MU over CB. Now MU, we just got that, it's 526. As for CB, now CB was given in the problem as 1.67. I want to talk about that here in a second. But CB was given as 1.67. If you see that right here, I want to talk about that here in a second. So, but for now, we'll just take the value 1.67. And when you chug that out, you're going to get 314.97 foot kips. So we're going in with LB is 10 feet and MU over CB as something basically like 315. Okay, now I want to talk a little bit about that CB value. Let me erase this. So I want to talk about that because I want you to have some appreciation as to where that's coming from. So first off, let me pull up this little Excel sheet I made. Okay, so this is an Excel sheet I made to look at the CB value for this problem. So if you remember, here's our beam that we're looking at. We've got a simply supported beam with a concentrated load at midspan and a distributed load. Now, here's the thing about the CB values. If you scroll down here, there isn't a case like that. They're either just concentrated loads or they're just distributed loads. This has both, okay? Now I'm just saying it's 1.67. Why am I doing that? Well, what I'm doing is I'm making a choice, okay? And I'm choosing to consider only the concentrated load. I'm basically choosing to ignore the distributed load when I'm computing CB. The reason why is the magnitudes, okay? Here's the problem here, and just take a look at the magnitudes. Think about this, critically. The beam has 65,000 pounds at midspan, right? And the only dead load it's holding up is its self-weight. That 65,000 pounds is definitely going to be much more of an impact than the beam self-weight. That is definitely driving the design. You also see that in the numbers, right? Remember, if you look at our moments, so look right here. This is the actual computations that you can do. Now, if you look at your dead load moments, look at some of the values that we got, okay? We got a dead load moment of 5 foot kips. Remember, that's what we got before. And a live load moment of 325 foot kips, right? There's much more live load moment than there is dead load moment. But if you actually wanted to compute CB, I want to show you how you would do that if you had mixed loads. So if you had a distributed load and a point load and you wanted to accurately compute CB, here's how you would do it. So first off, what you would need is your moment diagrams. You would need the dead load moment diagram and the live load moment diagram. Now what I'm doing is I'm doing this at every 2.5 feet, because if here's your beam, right? Here's your beam, and if I wanted to compute CB for a given segment, let's take this segment. What I need is I need the moments at quarter points, so at 5 foot, 2.5, 7.5 foot. So I need 2.5, 5, 7.5, and then I need M max, which just by observation, looking at that, is right here. So I need moments at every 2.5 feet. That's why I reported it like this. And so what you would do is you would basically plot your moment diagrams for the dead load. So you can see, here's my dead load moments, here's my live load moments. How do I compute those? I just use the formulas in the manual, right? So, or I could use statics, either one works. So for a simply supported beam with a uniformly distributed load, so for the dead load, Wx over 2 times L minus X. So look at what I've got here in the Excel, Wx over 2 times L minus X. So I'm just computing that like I would any dead load moment. For the live load moment, I'm just using the formula here. You can see it's a linear moment diagram, and the moment diagram is just Px over 2. So Px over 2. Once I've got the dead load moment and the live load moment, I factor them row by row, 1.2 dead plus 1.6 live, and now I've got my terms for CB. I've got my MA, my MB, my MC, and my M max. Now, once you take a look at these, you look at your CB value. The CB value is only 1.661, or it's 1.661, but I used 1.7. Well, 1.7 comes from when you basically consider that the dead load is negligible. If I were to take this dead load and set it equal to 0, it goes to exactly 1.67. But the more dead load that you apply, the more that 1.67 becomes inaccurate. So if I put a lot of dead load on this beam, if I put like 5 kips per foot, well now 5 kips per foot, that's a lot of dead load. That's a lot of distributed load. So that combined with the live load, now we're starting to get an impact. So I guess the overall takeaway is you can use table 3.1 with mixed loads if those loads, those other loads are negligible. But if they start to have a profound impact, you kind of need to go through the process of computing your CB. So hopefully that makes sense. Again, if anybody has any questions, you can feel free to ask me on Teams, or we can talk about this on Wednesday or during the final review. So let me go back to the calculations. So let's go back here. So we have an LB value of 10 feet and an MU over CB of 314.97. Now I want to show you what I've got down here. So if you remember, I said you're going to have to do a lot of page flipping. I kind of cheated a little bit because I've got the table 310 and the table 332 all on the same page. So I'm kind of cheating a bit. But if you want to follow along with me, I've got the bookmarks. I put the page numbers up here in the screen clipping. So this is 3-117 and 3-25. Again, what I would do is maybe get 2 bookmarks and prepare to do that a bit. So what we're going to do is we're going to find that point on the chart. So what are we doing? We're going to go in shapes, put a line. We're going to put in a line, maybe like right here, something like that. Hope that's not snapping, and then another line, sort of like that. So you can see that's about at a length of 10 feet and about a moment of 315. I think it's a little off of 10 feet, but it's close enough for our purposes. And so now that I've got that, what I'm then going to do, let me go over here. Now what I'm going to do is I'm going to pick a trial shape, okay? So what I'll do is I'll take this point, that point right there, and I'm going to go up and to the right, okay? I'm going to go up and to the right. And the first section I see is a W21 by 48. So maybe what I'll do is I'll start a little table down here, and like we had on the slide, and I'll say, okay, trial. And so the first one is W21 by 48. Now what I'm doing is I'm comparing the MU of, and I'll just write one big MU of 526 against the phi MP. I tell you what, let me not write a big 526. I don't want that to be unclear. Against the phi MP. And so this is where, okay, well, what is the phi MP for a W21 by 48? Now you got to flip. You got to go back to table 3.2. And so we're going to look at the W21 by 48, and we're going to find its phi MP. And its phi MP is 398. So 398. And so is this section okay? Let me put the units on here. Is this section okay? No. This section is no good. It's no good because I don't care what we do in our calculation. That moment capacity will never be larger than 526. And to be clear, what we care about is the actual moments, which are 526. We don't care about comparing this to the 315 or the 314.9 value, because that's just a value that we go into the table with. The actual moments on the beam are 526. That's the actual maximum moment at midspan. So is the W21 by 48 going to work? No, it's not going to work. Okay. So the next thing that we do is we just go on to the next shape. So we go back to our chart and we say, okay, if that one doesn't work, what about the next one? So let's go up here to the next one, and I think that is a W18 by 55. Okay. Again, this is 526. What about the capacity? We'll go over here to the table, the W18 by 55, and again, I'm looking over here, so this would be you flipping in the manual again, and that capacity is 420. Again, no good. Okay, so keep going, you know, and again, you might have to do this a few times. It's just the nature of the problem. Okay, now we've got, what is this? I'm sort of seeing a couple lines here. We might look at both of them. We've got a W21 by 55 and a W18 by 60. I'll look at it in order of weight. So this is both 526, 526. So let's see if we can find these. So the W21 by 55, that one's bolded, but the W18 by 60 is not. Again, it's possible that you don't find a bolded row. And so both of these, unfortunately, though, are too small because we've got 473 and 461. Oh, that was a little sloppy. Okay, so let's see. Let's keep on going. And again, it's possible that you keep on going here. Now, we could try the W14 by 61, but I can see that over here. I don't know if you can. What about this one up here? Let's see. We keep on going. That. The W21 by 62. What about that? So let's try the W21 by 62. Oh. Okay. Now the W21 by 62, that one's that right there. And look at that. Look at its VMP. Its VMP is this right there, and it's 540. So now we've got something going on here. We don't know whether or not it's okay. We have to go through and do the math and check it. But now it's worth looking at. Now, before I waste all the time doing the math, though, I am going to do one more thing. I'm going to check the IX required against the actual IX. So the IX required for this one was, let's see, what was it up here? It was 968.3. See, I just didn't even bother doing it for the other sections because there's no point in looking it up because it doesn't matter. So that's inches to the fourth. Inches to the fourth. And now, if you look at the W21 by 62, this is the W21 by 62. Its moment of inertia is 1330. And now it looks like we're on to something. So I don't put the units there. I put okay. Now we're on to something. Now it looks like we're cooking with fire here, because now what we've got is we've got a situation where we have a section. We're pretty sure it meets the deflection requirements. I mean, assuming we didn't make any calculation errors, that it'll meet the deflection requirements, and we're pretty sure it's going to meet the moment requirements. There's still a possibility it doesn't, because even though we have a section that we think works, that CB value, if we actually compute the capacity, it could still be under 526, but we have to do the math to check. But now it's at least worth doing. So let's go through and analyze that trial section. So step 5, analyze the W21 by 62. And again, other than that iterative approach, everything that we're doing here is the exact same as the example that we did in our previous lecture. We're still going to go through it and check all of the math. So I'm going to write some properties for the W21 by 62, and I'm just getting these from up here. So for instance, the LP is 6.25 feet, the LR is 18.1, etc. I'm going to write all those here. So LP is 6.25 feet, LR is 18.1 feet. And remember, for our beam, LB is, again, 10 feet. So that means we're in zone 2. And in design land, more often than not, you will be in zone 2. That is highly common during the design phase. So in order to do our design, we need to recall our CB. Again, that's 1.67. We need to recall, we've got LB. We need VMP, which we just wrote down up here. We just, in our table, that's 540. We need our VBF, which the VBF for this section is 17.5 kips. Again, just got that from table 3.2. You can see that right there. You can see here's my, here's the VMP, here's the VBF, the LP and the LR. All that stuff's just coming from the table. We also have the VVN here and the moment of inertia. So it's all just coming from there. All right. So now that we've got all of this, we can compute the following. So remember, we compute this, which is, when you chug that out, 792.2. We compare it with this, which is just 540. And therefore, VMN is just the minimum of those two, and the minimum of those two, so I'll just write it like this. is 540. And when you compare that against MU, and MU is 526, we know that that's okay. And a couple other things that are worth pointing out. So number one, if you want a performance ratio, I went ahead and computed that. 0.974. So I just took MU over VPN. So that's a pretty efficient design. But the other thing that's worth pointing out that we kind of glossed over is this number right there. That 62 is 62 pounds per foot. That's lighter. Get ahead of myself. That's lighter than the assumption. Because it's lighter than the assumption, we actually don't need to go back and update these moments from up here. We can if we want, then there's not a terrible reason not to, but if it can hold up the MU at 526, it can certainly hold up its actual MU because its actual MU is going to be less than that. So we know it's good. I'll show you here in a second. I'm going to pull up some Excel and show you what happens if you update that. Now, for shear, all we have to do is compare its phi, V, and X, which if you look that up, you'll get 252 kips to its VU. VU is 53.2 kips. So we know that's okay. And I have a performance ratio there of 0.211. Again, shear never really matters all that much. Really a small impact. And then lastly, if we want to compare our deflection limit of 0.667 inches against the actual deflection of PL cubed over 48 EI, what we would do is do that deflection calc all over again, 65 kips times 20 feet, use the actual length, not the unbraced length. And for the moment of inertia, just use the actual moment of inertia of the beam, which the moment of inertia of the beam, we looked that up, was 1330. So 1330 inches to the fourth. And when we chug this out, we get 0.485. So that's okay. Because 485 is the actual deflection, and we're limited to 0.667. So we're under the limit. We're good. And if you want, you can also compute a performance ratio. Just take 0.485 divided by 0.667, and you get 0.728. And that's it. So that's your answers. Well, I guess I should clarify, what is your answer? That's it. That's your answer. Use a W21 by 62. And that's it. So, because we checked moment, checked shear, checked deflection, we arrived at a shape based on successfully iterating through potential options, and there you go. So hopefully that's pretty good, and I'm hoping that throughout the video you were pausing and kind of seeing if you could repeat those calculations, because a lot of it is pretty straightforward. I only have two other things I want to show you. First off, I wanted to pull this spreadsheet that I made. One of the things I did in the spreadsheet is I actually went through and repeated all of the calculations. So everything that you're seeing here, you can see the performance ratios that we got, all the values that I computed, it's all the same. All of this was based on an assumed weight of 100 pounds per foot. Now, again, I said that you don't need to update the moments, because if it can hold up 100 pounds per foot, it can certainly hold up 62 pounds per foot. But if you would like, what you can do is update that And what it's going to do is it's going to affect all of your computations moving forward, but not very much. So instead of an MU, for example, of 526, the MU is going to drop down just slightly because the dead load drops slightly. And so you can do that in Excel if you'd like. You see it doesn't really affect anything all that much. But if the beam is heavier than what you assumed, then you really do need to do this because it's possible that it doesn't work. Okay, let's close this up by talking a little bit about shear. So we haven't talked about shear explicitly, and I want to talk about how you compute phi/Vn, because for the vast majority of beams, it's very easy. You just take Fy times the area of the web, the depth times the web thickness, and you multiply it by 0.6. So I'm going to get my little rubber I-beam mock-up because I'll use that once again today. So let's talk about shear. So I want to first talk about shear stresses. So up until now, I think that hopefully we're starting to get comfortable again with sigma equals my over I. So y is measured from the centroid, I is your moment of inertia, and m is your applied moment. So as you apply moment, the flexural stresses increase linearly. At the centroid, the stresses are 0, and then they increase from there. So the important thing to keep in mind about sigma equals my over I is that expression, that concept doesn't change if you're looking at a rectangular beam or an I-beam. It doesn't matter. It's always going to be the same stress distribution. Now for shear stresses, the formula is a little bit more complicated because you need the shear, you need the moment of inertia, you need this term Q, which is the first moment of area, and you need B, which is the width of the beam. Now I'm going to somewhat skip the computation of how you would actually get the shear stress profile that you see here on the right. But one of the things I want to point out is what happens between like a rectangular beam and versus an I-beam. And one of the things that you see is what happens right here. Because here you go from a beam width of this to a beam width of this. The beam width suddenly changes. So if the stress profile is mapped by this equation, and B suddenly gets smaller, what happens is the shear stress suddenly gets larger. So when you look at the shear stresses on an I-beam, you find that the shear stresses are very, very high in the web, in the central portion of the web. So whenever we look at I-beams, whether they're rolled W shapes or whether they're plate girders, and we're looking at shear, we look at the webs. That's what we focus on. And this is why, because the shear stress is primarily contained in the web. There's an old way of thinking about I-beams is that the moment is sort of carried by the flanges and the shear is carried by the webs. So when we look at a shear capacity for I-beams, we mostly focus on the web and not the flanges. There are a couple of limits in some of the bridge spec where you have to look at the flange size, but by and large, the web is what matters. And in general, we have two primary concerns. We either have shear yielding, and so shear yielding is just taking the entire web, so the area of the web, D times dW, and having it reach its maximum stress, which is the yield stress multiplied by 0.6. There's that von Mises 0.6 popping its head up again. The other item is what's called shear buckling. Shear buckling tends to be a phenomenon whenever you're dealing with plate girders. I have a video here. This is a really great test of a beam and shear. Let me find it right here. There we go. This is a really good video of a plate girder test. You can see they've got a load right here on the top right, and it's being supported here on the top left. So there's a lot of shear. It's actually a stainless steel girder, but I kind of like the test because you can see what happens in shear. Because what's happening is, I'll pause it right here. What's happening is, I don't think I can draw on this, but if you look this way, like this way right here, it's being yanked on in tension, but this way, it's being pushed on in compression. So the web sort of buckles and folds that way, and so that's kind of the shear buckling phenomena that you get in plate girders. Now, what you can do to fix that is you can add stiffeners. So if you ever look at the difference between an unstiffened web and a stiffened web, those transverse stiffeners basically are taking that buckling length and they're making it shorter, and they're improving the capacity. So if you ever look at, for example, older plate girders, you'll see shear stiffeners kind of like all over the place. But that's the difference between an unstiffened web and a stiffened web. If you look at the capacity, and I think what I'll do is record a very quick example computing that capacity, because I actually have a meeting starting here in a couple minutes that I want to make sure I meet on time. But the what you do in order to compute the capacity, it's very straightforward for W shapes, is you first have to determine what your phi value is. And in most cases, phi is 1. There are some cases where phi equals 0.9. Now, if you're doing a plate girder, all of this is up in the air, and you have to go through and do all of these calculations. For W shapes, what ends up happening is because the way that we compute, or the way that we manufacture W shapes, the webs are so stocky that you end up having so much shear capacity. It's also reflected in the equations. The way the spec reads, it says that for all provisions in the code, phi is 0.9, except for these cases governed by a particular section. But that's all the W shapes. If you look at the W shapes, and particularly you focus on this note, like every single W shape except for about 8 of them, phi is 1 whenever you're dealing with 50 KSI steel. Other than those are the ones where phi is 0.9, but everything else, phi is 1. And in order to compute the capacity, all you do is you take 0.6 times Fy times the area of the web times this term CV1. CV1 is it's a constant that you multiply your capacity by to account for the potential for buckling. But if buckling isn't going to occur, then CV is just 1, so you're not really doing anything to the capacity. And you compute CV1 just based on a slenderness check. It's kind of akin to what we did with columns. You know, you compute the slenderness and you compare it against a given limit, and dependent upon that limit, you've got a various expression for CV. And CV is really straightforward to compute. What I'm going to do in a follow-up video is I'm actually going to compute PVN for a given shape. I'm going to do a W24 by 62. The W24 by 62, you can see the shear capacity, and when you compute it, you'll see that it matches, you know, to the T, and it's a really simple calculation. But I'm going to do that in a follow-up video because I'm actually running short on time for a meeting I'm joining. So I will see you all in class on Wednesday. That's all I have.